Small sample hypothesis test, example 5a. In a sample of n equal 4 tosses of a coin, the proportion of the heads, p hat, 3 out of 4, or 3 divided by 4 is 0.75. If the coin is evenly weighted or fair, the proportion of heads in the long run should be 0.5. So we should have equal numbers of heads and tails. And the proportion of tails, q 1 minus p would be 1 minus 0.5, which is also 0.5. Okay. And we want to test whether the coin is unevenly weighted at the alpha equal 0.05 level of significance. So we want to test h naught, p equal 0.5, coin is evenly weighted, versus h1, p is not equal to 0.5, the coin is not evenly weighted. So this is a two-sided test. The coin, we have a not equal to symbol here, because a coin would be considered unevenly weighted if the proportion of heads was either more than 0.5 in the long run or less than 0.5. Okay, so again we want to check that n times p and n times q are both at least 5. If so, then we can use the z table as kind of a shortcut. Otherwise, if not, we have to use exact binomial probabilities. So n times p, the sample size is n is 4. P is that's the value of p if h naught is true, is 0.5, and that's equal to 2, greater than or equal to 5, and that's a no. Okay, and then we can also use compute n times q. Q is also 0.5, so that's equal to 2, not greater than or equal to 5. That's a no. Okay, so in order to use the z-table, we need 2 yeses here. We have 2 no's. So a yes and a no is not going to work. A no and a yes is not going to work. We need 2 yeses before we could use the z-table. So we'll have to use the exact binomial probabilities. And so we'll use a tree diagram to do that. A full tree would have 16 paths, and we could do the 16 paths, but really we only need to show the paths for which either the proportion of heads is greater than or equal to p hat, so greater than or equal to 3/4, or the proportion of tails is greater than or equal to 3/4. So we want to include either extreme, because this is a two-sided test. And because in the long run the coin would not be evenly weighted if there are either more heads than tails or fewer heads than tails. Okay, so so we're going to set up the tree as if h naught is true. Because the probabilities are all going to be the same, p is 0.5 and q is 0.5, we don't really need to put the probabilities in the tree because they're all the same. Okay, so the first toss is either heads or tails, and they're both have if the coin is evenly weighted, we have an equal chance of getting a head or a tail. So they're both 0.5, but we don't really have to write that in the tree. So that's the first toss. And the second toss, again, is either heads or tails. And so we have 4 possibilities. We can have head, 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 tail, tail, head, tail, tail. Third toss is also either heads or tails. So the third toss, either heads or tails. So we have 8 possibilities: head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. Okay, so fourth toss also either heads or tails. Head, tail, and for this path here, this actually would be the third path on the tree. we already have 2 heads and 1 tail, so we don't have to include. We're only going to include the paths where we have 3 of the same. You can make the full tree if you want, but we don't need to include the path where we have the 4th toss here as a tail, because it will have 2 heads and 2 tails. We're only looking at the paths where we have 3 of the same. So we could just do the one path there, the head, head, tail, head. Again, we could just do the head here. We don't need to do, if we do the full tree, we'll also have a tail, but then, but we're only looking at the paths where we have 3 of the same. And this one here, we'll make that a tail, okay? Because we're only looking at the paths that are 3 of the same. This one here will be a head, head, tail, tail, head, tail. So the next one will be a tail. Tail, tail, head. That will be a tail. This one could be either a tail or a head. We already have 3 tails. So let's see, head or a tail. So I'm just doing a little shortcut for the 4th toss. I'm not writing down all the possibilities, but just for convenience, I'm just writing down the possibilities where we have either at least 3 heads or at least 3 tails. Okay. So so all these probabilities are going to be the same. It's going to be 0.5 times 0.5 times 0.5 times 0.5. So it'll be, if you multiply those out, that's going to be 0.0625. They're all the same. So this is 0.0625. These probabilities are all going to be the same. So do 0.5 times 0.5 times 0.5 times 0.5. If you want, we could also write down what these represent. That maybe it will help your understanding. So the top path, we have 4 heads. And then the second path, we have 3 heads followed by a tail. 2 heads, a tail, a head. A head, a head, a tail, and 2 heads. Head and 3 tails. A tail and 3 heads. Tail, head, tail, tail. Tail, tail, head, tail. This will be tail, 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 head. And this bottom path, all 4 tails. Okay, so those are the paths where we have either at least 3 heads or at least 3 tails. If we add these up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 paths. So we just 10 times 0.0625 is going to be 0.625. So our p-value is going to be of 0.625 is greater than alpha, which is 0.05. So that means we fail to reject H naught. A sample does not provide enough evidence. Evidence to say the coin is unevenly weighted. it looks like, I mean, it could be unevenly weighted. We did have more heads than tails. Proportion of heads was more than 0.5 in our sample proportion, but it's a small sample, and it's quite possible we could have gotten result that extreme even if the coin is evenly weighted. So anyway, our sample was just not big enough to draw a firm conclusion there. Okay, so let's we could also in my lab sometimes they have you fill out a little table, so we could put these paths in sort of a table form, and they want you to fill in the missing path here. So we noticed that there's five paths that start with heads, and there's only 4 listed here that start with tails. So the missing path is going to be it's going to start with a tail, and if you look at and it's going to be we already have a tail followed by 3 heads, so there's going to be 3 tails, and the question is where the head is going to appear. So we already have a head followed by 3 tails. We already have a head in the second position with 3 tails. We already have a head in the third position with 3 tails, but we don't have a head in the last position. So it's going to be tail, 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 head. And the probabilities are the same. It's 0.5 times 0.5, 0.5, 0.5, which is 0.0625. Looks like I'm missing a decimal point for some of these. These should all be 0.5. Okay. And the p-value then is the total, which would be 0.625. So in my lab, and the conclusion is the same. There's not enough evidence. The p-value, this is the probability of getting a result this extreme if h0 is true, and that's a pretty high p-value. Again, we can make a diagram showing 4 possible outcomes of hypothesis testing. Either h0 is true, or h1 is true, and either we don't reject h0 or we reject h0. So there's 4 possible outcomes here. h0 could be true and we don't reject h0. h0 could be true and we reject h0. h1 could be true and we don't reject h0. h1 could be true and we reject h0. So if we reject h0 and h0 is true, that's called a type 1 error. And they use the Greek letter lowercase alpha. It looks like a little bit like an A. To represent the probability of a type 1 error. Usually, well, the alpha is set by the researcher. We'll usually use 0.05 for alpha. 0.01 is another commonly used value for alpha if you want to be very sure that you're not making a type 1 error. And then the confidence level is going to be 1 minus alpha. So if we have if our alpha is 0.05, then our confidence level would be 0.95. So that means we would be 95% confident of our conclusion. If we don't reject h0 and h1 is true, that's called a type 2 error. And the Greek letter beta, that looks like a B, is used to represent the probability of a type 2 error. It's actually sort of a script capital B, and then 1 minus beta is called the power of the test. Okay, so I put the terminology down here. 1 minus alpha is their level of confidence. Usually it'll be around 95%. Alpha, Greek letter alpha, is our desired level of significance. I like to call it the level of doubt. Usually we like around 5% doubt. The p-value, it says here the actual level of doubt, but more precisely it's the probability of getting a result this extreme if h naught is true. And beta, the Greek letter beta, looks like a script capital B, probability of a type 2 error. Usually beta is not computed because in order to compute beta we need a specific value for P and the alternative hypothesis. So usually we have a greater than symbol or a less than symbol or not equal to symbol in the alternative hypothesis rather than a specific value. So beta is usually not computed. 1 minus beta is called the power of the test. Because we failed to reject h naught in the above example with a p-value of 0.625, what type of error might we be making? I'll give you a minute to think about it. So if we don't reject h naught, we take a chance of a type 2 error. If we reject h naught, we take a chance of a type 1 error. But this example here, we did not reject h naught, so that means we take a chance of a type 2 error. So we might be making a type 2 error. Okay, so let's redo this example if the proportion of heads was 4 out of 4. So again, we don't need to do the full tree. We just need the paths with at least 4 heads or at least 4 tails. And so there's only one path, or actually 2 paths that we need to consider. Either the head, or tail. We need to look at both extremes. Again, these probabilities are all 0.5. Usually when they're all the same, I don't write them in, but I'll write them in here. These probabilities are all 0.5. And if we multiply straight across, 0.5 times 0.5 times 0.5 times 0.5, 0.0625. And so the p-value here is going to be 0.125. Is that right? 5 and 10 carry to 1, 5. Yep. Okay, so that's a lower p-value. It's still not enough to reject h naught. So this is the p-value of 0.125 is greater than alpha, which is 0.05. So so again, we fail to reject h naught. Sample does not provide enough evidence. Enough evidence. That the coin is unevenly weighted. Okay. Example 5c, find the p-value of the proportion of heads is 6 out of 6. Okay, so again, we only need to look at the 2 extremes. The whole full tree would have, keep in mind that each time you add a toss of the coin, the number of paths doubles. So for 4 tosses, we had 16 paths, and then if we have 5 tosses, you double that, it's going to be 32 paths. And for 6 tosses, double that again, it's going to be 64 paths. So it should be taking up a lot of paper if you make a full tree, but we only need the paths with either at least 6 heads or at least 6 tails. So there's only 2 paths again. And the probabilities are all 0.5. So we have 6 heads, and or we could have 6 tails. So it's going to be 0.5 times 0.5 times 0.5 times 0.5 times 0.5. So okay, so maybe I'll do that on a calculator here with this many. So it's 0.5. Actually, you could do 0.5 repeated multiplications, or you could use the exponent key here, the exponent 6. And that's 0.015625. So the p-value would be the total here. 0.03125. Okay, so in this case we would reject H naught. So getting 4 heads in a row is not all that unusual. It's a little bit unusual, but to get 6 heads in a row, if the coin is unevenly weighted, we would reject H naught and conclude that the coin is evenly weighted. Reject H naught with 95% confidence and conclude coin is unevenly weighted. The 6 heads in a row is unusual enough that we can start to think, well, maybe this coin is not evenly weighted. And that concludes this presentation.